Hi guys, so we're going to do a bit of astrophysics now between Stefan's law and Wien's law. So Stefan's law is quite a nice one. It just tells us about the power or the luminosity of a star is equal to Stefan's constant, that one's on your data sheet, times its area, times its temperature to the power of 4. Okay? So the way we can find its temperature is actually by using Wien's law. Okay? So Wien's law is saying that the wavelength max times the temperature is always equal to a set constant. So let's say we have a graph here. So what we do is we can model stars as black bodies. So what a black body is, it's basically a perfect emitter and absorber of radiation. So that's when we get a smooth curve showing it's like black body curve, okay? So again, stars, we see the curve is because it's a black body curve. If I want to figure out the temperature of each star, what I do is I see where the peak is, wavelength max, take the peak and I go down to see what that wavelength is. And for the blue one, again, we find where the peak is, that peak intensity, and we go down to see what that wavelength is. So now we can calculate the temperature of both of those stars. So to calculate the temperature of our black star, what we're going to do here is we do 500, check your axis, nanometers times 10 to the negative 9, times the temperature is equal to 2.9 times 10 to the minus 3. So I can figure out where the temperature is. So all we have to do is 2.9 times 10 to the negative 3, divided by 500 times 10 to the negative 9. And we get a temperature of 5,800 Kelvin. Okay, so that's the temperature of this star. So again, 5,800 Kelvin. Okay. For our blue star, we're just going to get a slightly better pen because that blue's run out. For our blue star, what we're going to do is our wavelength, and we can see our wavelength there is 1,000. So 1,000 nanometers times 10 to the negative 9 times its temperature is going to equal to 2.9 times 10 to the negative 3, that constant. So I can solve now for that temperature is. So all we do again is 2.9 times 10 to the negative 3 divided by 1,000 times 10 to the power of negative 9 to figure out our temperature there is going to be 2,900 Kelvin. So 2,900 Kelvin. Now we can also figure out what type of stars they are, what spectral class they are. And if you forgot spectral class, you need to watch our earlier video when we talked about the classification of stars. So our spectral class, if we're around 6,000 Kelvin, that's around the temperature of our sun, we know our sun is a G-class star. And if we're around 2,500 Kelvin, this one's around 2,900, we know that's being an M-class star. Just a reminder of your classification. Remember, it's O, B, A, fine, girl, kiss, me. And if you want to look at those temperatures, those ranges, that's just on an earlier video. So again, we can find out now what classification its star is because we know its temperature. And once we know their temperature, we can then figure out, if we know its luminosity from observing it, we can figure out what its area of that star is. Or if we know what the area is, we can figure out what its luminosity is. So you can see how we use both laws together to either figure out what the area of the star is, if we know its luminosity from its apparent magnitude, what we're observing, or to figure out what the luminosity is if we're trying to theorize a star with a certain area. So other things you might see in exam papers is sometimes you might see that instead of being a smooth black body, you might see some indents in it. So what these are called, these are absorption lines. So if we've got absorption lines, normally the only absorption lines you need to know about is your Balmer lines, your hydrogen Balmer lines. But absorption lines, what they tell us about is, let's say we've got your star, so there's the core of my star, and my star is emitting light. Instead of that light reaching us on Earth, so we have our telescope to see it, what might happen is you can see it's passing through the atmosphere of the star. And as it passes through the atmosphere of the star, there might be some hydrogen there, or some helium, some type of atoms present, and they're going to absorb some of that energy of light. Remember what happens when they absorb some of the energy of light, those electrons get promoted to higher energy levels. And that's why we've got gaps missing in our spectra. So we can figure out what wavelengths got absorbed. So remember, if it's hydrogen Balmer lines, we know that's because our electrons are starting in our excited state, in the n equals 2 state. And what happens in hydrogen Balmer lines is they get promoted, excited, or de-excite always down to that n equals 2 levels. So that's always going to be your hydrogen Balmer lines. Okay, so it can tell us about what is present in the atmosphere of that star. And hopefully remember, if there is some of these hydrogen Balmer lines present in that spectra, in that curve, we know that it must be an A-class star because hydrogen Balmer lines are most prominent in our A-class stars. And those temperatures are around 10,000 Kelvin.